My name is John Crepezzi. I've been doing Rails for a long time at a bunch of different companies. Similar to last year, I started writing this talk and then I ended up with just way too much content. So I don't have much time to tell you about myself or my background, but you should just know that I'm pretty cool. If you're interested in learning more about me, you can consider following me. I'm cjohnrun on GitHub and Twitter. I'm also on mastodon.social. But I only have 3 followers, so I also try not to toot, in public very often. So, like a lot of you, I hope, I love Ruby on Rails. I love it even more than last year. Who here loves Rails more than they did last year? It's so great. It's a web framework that lets me easily and safely express my thoughts with no kind of unnecessary fluff, on top of a programming language that I still, 15 years in, find extremely beautiful. Last year, around the time of RailsConf in Portland, I left my job at GitHub, and after a brief misstep, here indicated by the crashing car, I now work at Jane Street, which is a tech-forward finance and trading company based in New York. At Jane Street, I continue to work on developer tooling, just like I did at GitHub, and it's pretty exciting because they have some of the best developer tooling that I've ever seen. They have robust systems for code review. They have really deep editor integrations, fast build pipelines, and they have some people there that just really know how their software works at a level that I've not been exposed to before. And what they don't have, sadly, is Ruby, and it follows that they also don't have Rails. Jane Street writes nearly all of their code in a fairly obscure programming language called OCaml. I've never worked in OCaml. I've never even known anyone that worked in OCaml. Not many other companies or projects use OCaml, and to be honest, before joining, I stressed quite a bit that I might be putting myself in some kind of a situation where I'd spend years investing my time in a skill that largely would end up not being transferable. When you first join the company, they put you through a 2-week onboarding to the language. It's they call it a boot camp. That's why this. It's not something you're going to want to miss because it's required and you have to go. But it's also something you will absolutely need joining the company. OCaml has some features and patterns that just don't make a ton of sense if you haven't been exposed to them before. Someone will walk over to you, and they'll probably reference the lambda calculus. You're going to make a confused look, and then they will hand you a book called Types in Programming Languages. It's pretty dense. They refer to it as TOPL. And they'll say something like, oh, it's a classic, or it's not as complicated as it looks. This is clearly a company that's thought a lot about what programming language they use and why they're using it. The impressions left on me were, first, that I need to keep an open mind and not just spend all of my time talking about Ruby and complaining. The second is that I needed to figure out what I didn't know and figure out how I could learn it. And then the last is that, given that Ruby and OCaml seem to exist in such totally separate worlds, what new tools could I gain that might apply in other places in my programming life? In this talk, I'm going to go over some neat things from OCaml, and I will show how they can be applied in Ruby. What I'm not going to do, the thing that I've seen talks like this do, is try to convince you that OCaml is somehow better than Ruby. As a spoiler, I don't think it is. This is. I convinced my wife to name one of our kids Ruby. As of this talk, I have no kids named OCaml. Rather, I hope to demonstrate that a lot of the things that we see as features in OCaml are actually design patterns instead, and with a little bit of work, we can have them in Ruby as well. The literal wall in my house is painted Ruby. Okay, so let's get started, and to set a good basis, we should probably just go over some quick similarities and differences between these languages. The first and most obvious difference is the style of the type system. Ruby's type system is dynamic, and OCaml's is static. For those of you that haven't programmed in a statically typed language, this means that the type of each variable is known before the code runs. So consider this example in Ruby. First, we define a variable called var, and it holds the integer 5. Then we redefine var. Now it holds 5, but as a string. Then we redefine it again. Now it holds var, but as a symbol. And then on the final line, we put something from params into var. Now we don't even know the type of it anymore. It could be a string, it could be an array, it could be a hash. We've all written code like this. It doesn't feel weird to me to write code like this. But what is the type of var? The answer is that it just kind of depends on where you are in the execution. Each line var is a different type. The type of the variable, so to speak, is only determinable at runtime. It's pretty easy for me to also write some code like this in Ruby. Here I am calling abs to get the absolute value of a string. This code, we can all look at it and we can know that it is probably wrong. In most code bases, abs is not defined on string. If in your code base you do have abs defined on string, please come find me because I want to hear about it. But that doesn't stop Ruby from us from writing this code in Ruby and it running it, and not until this part of the code is hit will we get a no method error like you see at the bottom. By contrast, in a statically typed language like OCaml, types are always known. We tell the compiler the types of things by adding these type annotations. They're essentially code that declares the type of all the variables. Who here has worked in a statically typed language before? Nice. You go and declare for each function as well what types they take in as parameters and what type they return. So here's a function called abs that takes in an int called n and then returns another int. You can't change the type of variables in OCaml. This isn't something where if you do it, you're going to get an error. Instead, the entire program will just refuse to compile. So here we're trying to define a variable that holds the integer 5 and then redefine it to hold the integer 5 as a string, and we get this, this error on compilation. Extending that a bit more, you actually can't even write code that mixes up types. Here I'm trying to pass our abs function to our abs function a string instead of an int, and the OCaml compiler stops us from doing that. OCaml has this really powerful type inference engine, and that means that you often don't have to write these types, but it's just really important to say up front that, again, every single thing in your code, the type is known before the code runs, as long as it compiles. Another big difference between these languages is the programming style or paradigm. To some of you who might be fairly new to programming, it seems like a pretty weird idea that I'm talking about programming style, as if I'm up here saying, like, I program fakey style, yo. Or my style involves lots of comments that have emojis in them. But these styles are paradigms. They're real things, and each as it was made was kind of a revolution in how code was written and reasoned about. Generally, the most common paradigms worth discussing are imperative, procedural, object-oriented, and functional. Of course, there are a few more. Everyone's going to debate you about the lines between these things, but these are the main ones that we'll talk about when we're talking about programming languages you might pick for an everyday project. Imperative languages like assembly and the original BASIC execute statements in order. There are no functions, and any sharing just involves jumping from one part of the code to another. That's normally done with something like jump or goto. And we can actually do this in Ruby. There's a library from Benjamin Bach that was written 15 years ago that lets you define labels and then go to them. So here we're defining a loop that'll print a string 7 times. And you can see we define a label called loop, and then we go to loop 7 times. Procedural languages like C organize imperative code into subroutines or functions. This allows us to better organize code, isolate variables into the functions they're created in, and also avoids this whole problem of being able to go to somewhere that is outside the scope of your program. Object-oriented languages like Ruby or Java organize behavior into objects and allow sending messages to those objects. So instead of having functions that take in parameters, there's kind of this implicit parameter called self, which makes it also so we have to refer to these as methods instead of functions, but same idea. This is an implementation of object-oriented, same thing. Functional languages like Haskell use functions as their primary organizational construct. So functions can be combined, they can be passed to each other, they can contain nested scope, they can call themselves. This is 2 examples of a functional style pattern in Ruby for the same loops that I showed before. You might be thinking, hey, wait, John, you said that there are these styles. You told me that Ruby is object-oriented, but then you showed me a bunch of code examples for all the different styles, and everything is in Ruby. And that's true, and it's because Ruby, as probably a lot of you know, is multi-paradigm. It supports all of these programming styles. It's just really good at being an object-oriented language. In fact, most languages these days are multi-paradigm. It turns out when a language comes out with a new feature, all the other languages want to have that feature too. OCaml is multi-paradigm. The O in OCaml actually stands for objective, which is a reference to the object-oriented nature of the language. It also has a specialty, though, and OCaml is decidedly focused on being functional. In the same way that Rubyists don't write recursive code very often, OCamlers, or OCamlists, or OCamlistas tend to kind of just completely ignore the object-oriented features. Aside from the code just looking different, this means that functional programmers are more likely to choose functions when approaching a problem, just like object-oriented programmers are likely to take things and simplify them by adding more objects or classes. Striking as these differences may be, the language has something very important in common, though. They're both expressive, and they're both, first and foremost, focused on making developers happy. Ruby tries to make developers happy by giving people the flexibility to express things the way that they want. For example, like the 5 versions of the code that we saw previously, and the fact that pretty much everyone in here could probably come up with 10 more versions of that code. OCaml makes developers happy by making certain types of easy-to-make mistakes no longer possible. It reduces the problem space that developers have to consider when writing or modifying code. And having worked in Ruby so long, I go to work and I tend to write OCaml with like Ruby glasses on. I try to create module interfaces that read like sentences. I'm obsessive about the separation of concerns for different parts of my app. And I spend a lot of time making sure that the code that I am writing is like testable. And then when I go home and I'm working on Rails and go back to writing Ruby, I've noticed that same kind of thing in the other direction. I'm looking at Ruby and I'm missing some of the features from OCaml that make me more productive, or make refactoring easier, or set my mind at ease about certain types of problems. So I think about those lessons, and I've been learning at work, and how they can translate back to Ruby and to Rails. Today I'll be covering 3 features, and for each I will go over what the feature is, how it works in OCaml, how something similar can be built in Ruby, and then, because we need to tie it back to Rails, I'll talk about how you might use it in a standard application. I should also issue a slight word of warning. If you're sitting in your chair right now and you're saying, I already knew that there's static types and dynamic types, this talk is boring. Well, this is where I just have to warn you that this talk started out pretty light, but it does ramp up pretty quick. And the pace gets pretty fast. I like really technical talks, but I do want to acknowledge that there's just a really lot of material that I'm about to go through. If there's something in here that doesn't quite make sense, consider coming back to the idea or playing with it yourself. Some of these things just they didn't click for me the first time around. They maybe took 20 times to figure out. So with that out of the way, the warning, let's get started on our first topic, which is probably OCaml's most fun-sounding feature. It's called functors. Pretty exciting. Thank you. In OCaml, there are basic value types. Think like a string, an integer, a map, an array. And then there are functions. Like I mentioned earlier, functions take in some number of parameters, and then they return something. So here we have a string called s, then we have an integer called I, and then we have a function called add, which takes in 2 ints and returns the 3rd int. Then there are modules. Modules are essentially groupings of functions that hold values that kind of do similar things in the same place. As a quick example, here's a module for describing a car wash. It can contain values like the price per wash, and it can have functions like wash, which in this example just takes a car, outputs a message, and then returns that same car. And as a side note, but a very important side note, these are not classes. There are no instances of car wash. The car wash itself has no state. The values on car wash can't be changed. You can't have a car wash with a different price. It's just kind of a bucket to hold loosely collected things together. And modules can be included into other modules in OCaml, just like they can in Ruby. And one of the primary ways that we avoid duplicating a ton of code for similar features is to include modules into other modules. So I might have a module describing blog posts and a module describing wiki pages, and I want them both to have short URLs. So I could introduce, just like in Ruby, a 3rd module that contains those methods, and I could share the relevant parts of the implementation. Many times when we do something like this, there are details about the behavior of the individual classes, like blog post and wiki entry, that need to be shared with has shortcode. So here we might get a short URL method back, but in order to get that, we have to give the prefix, right? So we're giving the blog post prefix as post dash and the wiki entry prefix as wiki dash. We do that because include doesn't take any arguments. So we need a way to get the information from the classes into the module, like has shortcode. There are two ways that we typically go about doing this in Ruby. The first would be to define methods with kind of like well-known names. You would define them on the including class, and then the module can assume that those methods are going to be there. So here we have the top module has shortcode. It's making an assumption that whatever module it's included into will define a class method called shortcode prefix. And then on the bottom, we have the class, and you can see that we're including the module, and then we're defining that requisite method. If we didn't define it, we're going to get a no method error. The second way to do this that we typically see, and the one that you'll see more often in Rails, but maybe haven't noticed or thought much about what it's doing, is to define a method like this, like has shortcode. When we do this, it gives you a nicer interface. We get to write one line, and we can pass the prefix directly into it. We actually make it a little bit nicer, too. We can get rid of this include has shortcode, and a lot of library authors will do this. It's a little crazy, but they will register a hook, and they will include the module directly into active record base so that when you go to use that module, you're just doing it with one line. The implementation of these methods normally looks something like this. We manipulate the outer class to store the attributes that we need. So we have the module has shortcode, which is an active support concern. It defines two class methods, one called shortcode prefix via the attr reader, and one called has shortcode, which is the one you use to kind of hook the behavior into your model. And then in the implementation of short URL, you can see that we are using the shortcode prefix and ID. So this is the same concept as the first way. It's just kind of all wrapped up in this nice one-line version. And when us library authors write something like this, we end up kind of littering a little bit of state around. The actual variable holding blog post's shortcode prefix variable lives directly on the class. So here we're looking at blog post instance variables. We can see that shortcode prefix is in there. And all of the methods that we define actually live on every model, even the ones that are not using shortcodes. So here we've defined another subclass of active record base called unrelated, and we can see that has shortcode and shortcode prefix, they're both there even though we're not using it. There are ways to fix this, but most libraries don't go through them, these methodologies. And if you look at AR base, you might just be surprised to see that there are a bunch of methods on there that you wouldn't expect. Of course, none of this is the end of the world, but functors, as I'm about to describe, provide a potential third approach. With functors in OCaml, which you can roughly think of as functions from one module to another, we can pass the details that modify the behavior of a module at the point that we're creating it. So this is an example from OCaml. On the top, you can see the definition of the functor. And again, read it as a function. It takes in a module called m, and then it returns a new module where the x property on the original module is now the same as the first module, but plus one. So it will modify and return a new module that is a varied version of the first module. If we could do something like this in Ruby, maybe we could use that behavior to kind of dynamically create a module that was modified in just the right way so that when we included it, it already knew what the prefix was. So can we do that? Well, this talk would kind of suck if I was like, no, we can't. So that's what we're going to do. What we're going to try to end up with is this. On the bottom, we have blog post, which is the class that we're trying to include into. It has methods like ID. Has shortcode is on the top. It's going to give us the short URL method. And then there's something we have to put in the middle, which will be the thing that it can hold on to the prefix. So to give us a hook into the point of inclusion, we could define a module method on has shortcode. And in this case, we'll call it make. Make will have access to the prefix, because the prefix gets passed into it. And because of the way that we've called make, we actually have the opportunity to return a new module instead of the module that was originally being included. Does this make sense? Are people getting this? OK. Creating the new module is trivial with module.new. And inside of that module, we can just include the original module. So like this code might be confusing and make some heads spin, but like we're not really doing anything here. What we're really doing is we're inserting that proxy module to give us a place to define the prefix method in the interim between ourselves and hash shortcode. We haven't added any behavior yet. Now we just have to define methods on the proxy module for each of the passed-in args. There are a couple ways to do this, but by far the easiest one is just use define methods. So here we're defining a method called prefix, and we return the prefix that we have scope on because we're inside of the definition of the make method. And boom, we can use this. This works. We can define a library using this pattern. We can use it with a single line just like before. And we can also demonstrate that the littering that I was talking about previously doesn't happen with this new method. So there's no instance variable sitting on blog post, and all of the classes that inherit from AR base that don't want this behavior don't get the extra methods. It's a little bit of a shame that this code is very specific to hash shortcode, but maybe it doesn't have to be. We can extract this entire concept into another module, call it functor. And all that functor module will do is have a method called make, which will work just like the previous one, except instead of only knowing about how to handle prefix, it'll just go over all the quargs and define methods for each of them. And when we do that, we get this behavior where we can use this functor pattern, extending it into any module that we're defining. And you can see inside of the short URL method, we have access to prefix, which comes from the proxy module. We also have access to ID, which comes from the base model. Another neat thing about this is that you can actually use this new version using functors to have the same behavior you would have before. So if you don't like the new DSL with the .make, you can just wrap that in a method called hash shortcode, and instead of doing the thing I showed previously, it'll just do a send include. So this feels like just a normal Rails API with all the benefits of the functor. This is a view of the main stage from the audience. Downstairs, you can see. And it provided a really nice place to put the title of the second section, which is on variants. This is the second feature we're going to talk about, and it's a language feature in OCaml. And with this feature, you can define a value where that value can be in one of several different states. So an example that's typically used is a color. Color can typically be expressed in a variety of different ways. We might express a color as RGBA, which is like red, green, blue, and alpha, or RGB, or hex, or name. This is a single type that can be any of those different representations. How would we do something like this in Ruby? Well, if it was me, what I would do is I would create a color class, and I would give it these factory methods for each of the individual ways that you can express color. So here we have a class that you can see in the initializer only knows how to deal with RGBA colors. And then we define these factory methods that essentially map the other color spaces onto RGBA. So we're essentially normalizing all of the colors that come in. In a lot of cases, this is the right answer. Probably a lot of you would write code like this. But it's not quite the same as the OCaml implementation because we've essentially thrown away the input that the user gave us. What if we had a feature where we needed to maintain a user interface that showed the color as it was input by the user? In order to do this, we need to somehow store information the way that the user entered the information. So the new problem is, how can we represent and store a color that might be in any of these different formats with our database? I hope we can all agree that single table inheritance is kind of like off the table for this problem. Making 4 tables for, or even one table with a type column is just, it's too much. What we want to do instead is we want to be able to put the color information into a single database column. So how can we do that without it getting really, really complicated? We can modify our color class to hold the details of the original input and determine the normalized color only when we're actually going to color something. It would look something like this. So instead of taking the RGBA and all of the different color types and normalizing them, we would actually send the of RGB method. When we call new, we would pass the label, which is the type of information stored in the column, and we would store the values, in this case, RG and B. Then in initialize, we would take in that label, and we would take in the hash of the details, and we'd hold on to them. And then we would go implement these 2 methods. There's one called toRGBA, which is the thing we could actually use to go color something in an interface. And then there is toHash, which is the one that we would serialize into a database field. And with this, we've mostly implemented the idea of variants in Ruby. A variant is kind of just like a label and then the data that is associated with that label. Of course, it's a little annoying that like you could pass any value to label, but you could theoretically fix that by making new private or something. Instead, we could go and formalize this pattern a bit more. We can wrap the whole concept up in a library that makes it easy to create and use these variant types and kind of ditches the need for us to use the factory methods at all. The way I think we'd want something like that to work is like this. So we'd have variant.create, which you would pass all of the different labels that are valid for that variant type. It would return you a new class. And then with that new class, you could call .new, pass it a label. And if you tried to create a new instance that used a label that is not valid for that variant type, it should raise an exception. So let's try to implement it. The implementation's pretty easy. In the create method, we can dynamically generate a new class, and we can set the labels onto it. When we dynamically generate a new class in Ruby using class.new, we're actually able to specify the parent class. So when we call class.new, it takes a single argument, which lets us say what the parent class of this new anonymous class should be. It's really convenient. We need that behavior because it gives us the perfect opportunity to have each of the different variant classes share some common logic. So when you create a new variant with an API like this, you would end up with color, which descends from P, just to be clear. The class you will receive is color, descends from P. In this case, the behavior that we want to share via P is the initializer. So you can see here how the initializer works, really straightforward, takes in all of the different things that are passed to new with the special new ability to raise an invalid label if you try to create one with a label that doesn't exist for the variant type. Because OCaml is typed, though, they're actually able to go a bit further with these variants. The language supports a feature called pattern matching. So you can write code like this, which essentially you can think of as a case statement. And it is all the different ways that the variable can hold data. And when you use this pattern matching on variants, the compiler will actually make sure that you've handled all of the different cases that it can be in. It's called the exhaustiveness checker. And if you don't account for every type of color, then, like I said, with the other things earlier, the code just won't compile. The compiler is stopping you from making an assumption here. And in this case, the assumption is that not handling a case somehow means that it has no defined behavior. And the OCaml compiler actually has to have this feature. Remember when I said earlier that each variable has to have a known type at compile time, and that that type can't change? That means that normalized color, in this example, has to have a type. The type of normalized color has to be string. So what would you do when you skip, for example, the RGBA case? What value goes into normalized color? In Ruby, we might say nil, but nil has a different type than string, right? Nil is of the type nil class. So that breaks the invariant that normalized color has to have a known type at compile time. If you want to leave out cases in OCaml, you have to do it explicitly with a wildcard match. And that wildcard branch, by necessity, like I said, has to return the same type as all the other branches. Now in Ruby, we obviously can't make the code not compile if a case is missing. But can we get something like exhaustiveness checks to help us avoid adding new states for a given type, but then not handling it around our application? The interface we'll shoot for is something like this. We'll add a method on all the variant types on that class P, and we'll pass it a hash where the key of the hash is the label that you match, and then the value is a proc, and that proc is the one that you will execute in the case that the variable is holding a value of that label. The implementation of match is really easy. When match is called, we look at all the cases that are defined, subtract them from them the valid cases for the variant type, and if there's anything left over that we're not handling, we can raise an error. We'll just do that right here. We'll raise a unhandled match case error. Now we need to also handle that default case. To do that, we can just avoid raising in the case that the default key is defined, and we just fall back to the default key on the last line. OCaml actually implements two other things that I have to mention real quick. One is for the case that the match statement has entries that are not needed, that are not relevant. And those are cases where you have code that is dead that will never be called. So in that case, we're going to raise an extra match case exception. And the other is when you, kind of similar to that one, when you define a default case, but you've actually handled all of the different cases that could be present, that's another place where you have dead code. So we'll raise an exception for that too. We'll raise unnecessary default case. With this interface, you'll see errors at locations where cases exist but are not handled, which is common when you're adding a new label to an existing variant. Where cases are handled but they don't exist, which is common when you've either just removed something from a variant or a developer has somehow made a typo in their match statement. And also when instances are created from invalid labels, which is common when you've maybe typoed or you're mixing up the labels or you're mixing up the types of variants or you're removing cases, so you can identify dead code and go remove it. And if you use this pattern or something like it, you're actually kind of amping up your test suite, right? Because if you have light test coverage on a file, as long as that match statement is actually hit in the course of your tests, you've now got coverage for all of the cases. So you're actually using your tests as kind of like a proxy for the fact that Ruby doesn't have compilation. Okay. Whew. Now we're going to discuss the last feature for today, which is monads. Kind of fast forwarding through any inappropriate jokes, I have to come clean on a little fib that I told earlier, which is that I had said that the wildcard case of a pattern match couldn't return null because null is a different type than string. But in a lot of other statically typed languages like Java, that's not actually true. In Java, null isn't a type. It's a value that can be for any type. It indicates absence. This code makes sense, for example, in Java. String stir equals null. The value is null, but the type of this variable definitively and always is string. This is going to feel really familiar to Ruby developers, albeit that the actual thing that's happening in Ruby is super, super different from this. In Ruby, string and nil are completely different objects of different types. Nil is, like I said, of the nil class type. In Java, null is just the null value of all the types. The real reason that the wildcard case in OCaml can't return null is that null just doesn't exist in OCaml. It's not named a different thing. It's not called undefined or nil or something. It just doesn't exist. And at first when I heard about this, I was like, how? How can it be possible to have a language that doesn't have this? In some circles, null is fairly contentious. You probably saw articles that had this crazy headline at the top, $1 billion mistake. I think null is great, by the way. So. But it's worth quickly running down why some people are not very into it. And those two primary reasons are that there are no compile time guarantees for null. So you might have a variable that you don't realize could be null, and then you go access something on it, and you get a null pointer exception. The second is that the meaning of null has to be known on both sides of an equation. So if you have some kind of method for returning, for example, a bank account balance, and it returns an int in the case that there is a balance, and then it returns null in the case that maybe the account doesn't exist, that has to be known on the side that is implementing the function, and also known on the side that is using the function. That contract is more information that has to be known on both sides. For these reasons, OCaml just skipped over null entirely. But like I said, we need something like it. We need the idea that a variable can hold a value like an integer, or it can hold no value. This is a case where monads can come to the rescue, in particular a monad that we refer to as the option or maybe monad. Monads in OCaml are built using variants. Maybe it wasn't too surprising when I was just describing, we need a variable that can hold this or this, right? And variants are exactly that thing. The option monad has this shape. It can either be none or it can be some, and when it is some, it holds a value. So those are the two states that the option monad can be in. And just like we saw before with color, these option monads have their own type. So while 41 is an int, sum 41 is an int option. Sorry, I had to. The upshot of this is, that int option is completely a different type from int. If you take int option, that's the thing you're getting, not an int. But the most common, there are many ways to unwrap one of these options, but the most common one is a match statement. So here we have a match statement for handling an option, and you can see that we have to explicitly handle the some case and the none case. If we try to leave one out or we try to not do that, then the exhaustiveness checker is going to come yell at us, the code won't compile. So these are kind of similar to null values, but with a lot more work from the developer, with the trade-off being that you can't mistakenly introduce null pointer exceptions because you have to explicitly handle anything that could be empty in your code. Building something like this within the framework of variants that I described is pretty straightforward. We'll create an option module to wrap all the stuff we're about to do, and then inside of it we'll create a variant, which in this case I've called value, and it can either be none or some. This is just a variant so far, though. It's not a monad, so no one get excited. You know, this is just a variant, nothing great about it. Monads also have this other idea, which is composability. We typically talk about monads in terms of these two methods. They're called return and bind. So I'm going to try to explain how monads work in terms of those two methods. Return is pretty easy. This is an implementation of return in Ruby. And what it does is it takes in a value, and it wraps it in the variant. So in the case of the option monad, that means that we just take the value in. If it's nil, we'll return none. And if it is non-nil, we'll return some. So it's a variant essentially wrapping an individual value. And this is actually pretty neat because it's like an interplay of Ruby's being OK with null and this variant using null to express the idea of emptiness. The other method, bind, is a little bit more complicated, but not by much. Bind for a monad should have this signature. So it's an alpha option, and then it takes in a function, which is an alpha to a beta option, and then it returns a beta option. It took me like a really long time to even understand what that meant. So instead, we're just going to look at the Ruby implementation. But roughly what you can look at this as is we want to unwrap a monad and then send its value, in the case that it exists, into some context, which is a function like a block. Let that context execute, and then whatever its return value is, we want to rewrap it in a monad. So monad in, monad out. So to write that implementation in Ruby, we can build on the match statements that we implemented earlier. And we write a match like this, where the some case yields into the block that's been passed, the value, and the none case is just a no op. And then we do self.return at the end, which is not calling return, it's calling our implementation of return, which is a little confusing, but that rewraps it and makes it a monad again. And this works. We can now create options, and we can unwrap them using bind. So here we're creating an option for 42, which is going to return an option value back to us. And then we're able to call bind and pass that, and when we do, we get a block that yields in the value 42. We can compose multiple monadic operations together pretty easily, and the execution will stop after the first one that results in a none value. And on the second example here, we can also convert one option value to another option value without taking it out of its box. That's kind of what bind is for. So we send in an option of a certain integer, and then bind is able to add one to it in a safe way that automatically handles the case where xop is none. You might be looking at these examples and say, I already had a way to do these things, and they look like this. They're an if statement and the safe navigation operator in Ruby. And this is true. The safe navigation operator and if statements, though, it's possible for users of your API to ignore the case that something could be null. It's easy to get code that runs in the happy paths and does an error, and then one day you just like see an error because it turns out this thing you didn't expect just is null in the middle of your app. The option monad pattern, on the other hand, forces developers to have to contend with the fact that something could be null by having to explicitly unwrap it using bind. Now, I'm a Rubyist, and no one should write code like this, but there probably are some cases where this is valuable. If there's a case where not considering null could have disastrous consequences, this is a good pattern to use. It's also worth checking out the other common monads. Each one is kind of a design pattern that communicates more information to users about a given API and what to expect when dealing with the response. I feel like I always have this point in these talks where it's like, just breathe. You know, it's a lot of words. There's a lot going on. We've had a busy 3 days. I was out late last night. This is a lot. We went from not maybe even knowing that OCaml existed to learning about how it differs from Ruby, to tearing some of that functionality back across the line to something that we can imagine, conceptualize, and use in Ruby. I hope I've convinced you, if nothing else, that there's just like so much to learn out there. There's so much amazing things to read and things to do. And a lot of these concepts that we see as language features are actually just design patterns. In a language as syntactically flexible as Ruby, we can make them feel really natural. So like, go learn a functional language, or learn a logic language, a declarative language, learn whatever language you want. Not because you might switch, or because you're like done with Ruby, because you're moving on, but because it might make you a better developer. Find ways to bring those ideas back to our community and help me and help everyone here ensure that Ruby and Rails survive for another 15 years. Thank you, and I hope you enjoy the closing keynote.